Good morning, everyone, and welcome back to CS300 Introduction to Algorithms. Our plan for today is the last session before the final exam. Oh, super. So therefore today we're going to wrap up chapter 6 about string problems in string algorithms. Then we're going through chapter 7 about algorithmic paradigms. And in the end, there will be a short recap of everything we've learned in the entire course and some hints about the final exam. So that's our plan for today. And let me start the slides. Right, so we are talking about string compression, lossless compression, and we apply lossless compression to a sequence of symbols from the alphabet, which, for example, could be the alphabet of Latin characters or ASCII characters or Hangul characters, or any other actually kind of finite set. We could compress a sequence of bytes, we could compress a sequence of words. So it's kind of like a block compression scheme where every block is supposed to have the same length, for example, 8 bits, 1 byte. As long as the length is the same, then what we do here in Huffman compression is we assign to each element from the alphabet, to each symbol, to each block, sequence of bits of different lengths. That's the essential idea. In such a way that the frequent values of the blocks, the frequent symbols, get assigned short sequences of bits, whereas the infrequent symbols, the infrequent values of the blocks get assigned long sequences of bits. And the intuition is obvious. In this way, we can kind of shorten the length of the original string in terms of its number of bits, right? So encoding over variable sequence of bits. And that immediately raises the issue of delimiters. How can we, in uncompression, in the uncompression phase, how can an algorithm detect where one sequence of bits ends, where one code for one symbol ends and the code of the next symbol begins? Because it's now deliberately not aligned to bytes or words or whatever anymore, but it's really just a stream of bits from which the algorithm must somehow be able to recover the end of each encoded single symbol. And for that purpose, convenient way of avoiding having separate symbol for delimiters, we're going to restrict to prefix-free codes. The prefix-free code is a set of finite sequences of, let's say, bits in this case, such that no code is a prefix, a proper prefix of another code. So in this way, the issue of where one code ends and the next code begins does not arise, at least information theoretically. An algorithm still needs to look up the list of prefix-free codes in order to see where one code ends. But at least, yeah, then it is possible to detect the end of one code and the beginning of the next code. And a convenient way of expressing prefix-free codes is in terms of a binary tree, where the symbols to be encoded are in the leaves, and the bit sequences, the codes themselves, are the labeled, the sequence of labels on the edges on a path to that leaf. So here's an example picture where on the left you see such a complete binary tree. We consider binary trees because we consider binary codes. If we're interested in ternary codes, then of course we're going to consider ternary trees and so on. But let's, for simplicity, focus here on binary codes and as binary trees. And on the right, you see the table where with the induced assignment from symbols to finite bit sequences as codes. So, for example, the symbol D here is assigned the code 1010, which corresponds in the binary tree to the leaf D being reached from the path 1010, and so on. So yeah, this kind of correspondence is very helpful because now we can actually formalize the goal of lossless block or lossless string compression. Namely, the goal is to have the weighted length or the weighted depth, right? So the length of the code corresponds to the depth of the leaf in the tree. And the goal is to minimize the weighted length of the codes weighted by the frequency of the symbol. So frequency symbols have larger weight and infrequent sequence have smaller weight, so that the total length of the encoded original string equals the weighted length of the bit sequences, the weighted depth of the leaves in that tree. So we've considered this example string in the Latin alphabet, where we have already determined the frequencies of each symbol, which is easy to do algorithmically, right? Just make a table, an array, and count each occurrence, increment each occurrence while running through the string. That's linear time, so nothing deep here. But the challenge, the algorithmic difficulty, the goal is to determine such a prefix-free set of codes, or equivalently, complete binary tree, which minimizes this weighted length. So let's have a look at this expression. So this here counts how often the symbol S occurs in the input string. And this expression here expresses the depth of the corresponding symbol in the binary tree, which we've seen previously to coincide with the length of the binary code. So if a symbol S occurs 7 times, then multiply 7 by the length of its code and do so for every symbol occurring at all. This gives the total length of the encoded string of the bit sequence, the total bit length of the encoded string. And since we want to have an optimal code, that means minimize that overall encoded length. So this is now finally our algorithmic problem, which we want to solve. And to illustrate with this, to continue our example of the initial string with these sequences, frequencies, this gives rise to, for example, this code, to this prefix-free code, to this complete binary tree. There are also other prefix-free codes that achieve the same minimum weighted length, that achieve the same compression. It doesn't need to be unique, because you can already see here in the table that several symbols have the same frequency. So kind of replacing or switching symbols of same frequency could give rise to different codes. that still have the same minimal length. So let's look at this example. So for example, X is one of the least frequent symbols. So it's very deep in that tree, and it occurs only once, as often as does P. And the code of X is 10010. Indeed, 10010. And the overall length of the encoded string, you can now determine yourself. The important question is how to arrive at this or such a tree, complete binary tree, which is the same as how to arrive at a set of prefix-free codes for a given list of symbols together with given frequencies. That's only thing we need to know, the frequencies of the symbols, and then from that determine such a binary tree. And here's the algorithm, constructing Huffman tree algorithm. And the underlying idea is to build the tree up from leaf to the root. So the algorithm will take two symbols of least frequencies. Least frequencies means they can and will be most deep in the tree. That there will be leaves, right? Every symbol will be a leaf, but the symbols with least frequencies will be the deepest leaves. So we start with them building up the tree and combine two such symbols into the smallest possible tree we can imagine, namely a tree that has these two leaves as leaves, and we create another root to join these two symbols, to join these two leaves, and we pretend that we replace actually the two leaves with a root. So imagine in this example, X and P, these are two symbols with least frequencies, both frequency ones. And we combine them into a small binary tree, namely this one. See this binary tree. And we kind of remove and delete these two symbols from our list of symbols with our frequencies. And instead we insert another artificial symbol that is the concatenation, or the set of these two symbols, set with two elements, and assign to that set the frequency which is the sum of the original frequencies here. So if the original symbols X and P both had frequency 1, then this new compound artificial symbol XP combined will receive the frequency 2. And this is what is indicated here. So from now on, we pretend that X and P are not part of the symbols anymore. We've already dealt with them. Instead, the tuple X, P is a newly introduced symbol, now with higher frequency 2. And then we repeat that process. Again, extract two symbols of least frequency, let's say R and L, both frequency 1, combine similarly into a small binary tree, remove R and T and introduce a new symbol RT with frequency 2. And same for O and U. And then all symbols of frequency 1 have been taken care of. And in the next round of the Huffman tree construction algorithm, for example, we'll extract two symbols of least frequency being 2. For example, I has frequency 2, but the newly introduced symbol XP combined that we've introduced in the replacement for the two symbols X and P, this single new symbol also has frequency 2. So maybe there are different choices of how the next symbol is chosen, because there are many symbols that have least frequencies 2. But let's just say the next two symbols extracted here are I and the combined symbol XP, both with frequency 2. So they are removed from the list of symbols, and they are combined to form a new tree with the symbols IXP, right? The new symbol I combined with the newly introduced double symbol XP. And this new symbol is receiving frequency 4, as you see indicated here. And the next round, maybe H and S are extracted, combined into a binary tree whose root has the symbol pair HS of frequency 4. And maybe in the next round, these will be combined and so on, so that indeed this algorithm constructs a complete binary tree from bottom up, binary tree in such a way that the root and each internal node contain the sum of the frequencies of the of the lower levels. Yes, and yeah, that's a way of constructing the tree. And here's just an example. Okay, so let's start again. So here you see a tree being constructed. This is the end, and now we start again. I said we start again. Here we are, right? Here you see the table with the frequencies. The first two with least frequency are extracted. Then the next two are extracted and combined. Then these are combined and so on. Yes. Yeah, I leave it to you to follow the animation without my disturbing explanation. The end. Here you see the final binary tree constructed from the initial table with symbols and their frequencies. And from this complete binary tree, it's easy to then derive the prefix-free codes. So this is one example execution of the Huffman algorithm that constructs a Huffman tree, which is a provable, but we won't prove that here, a provable optimal prefix-free code for a sequence of symbols with given frequencies, integer frequencies. So this wraps up our chapter 6 on strings, string problems, and string algorithms. We've talked about mathematical formalization of strings and properties such as length, initial segment, which is same as prefix, and substring. We've talked about pattern matching problem and the Knudsen-Morris-Pratt algorithm for solving pattern matching in optimal linear time, linear in the sum of both the long input string and the short pattern string. We've talked about the longest common substring problem, which we've solved using dynamic programming as an improvement to the naive cubic time algorithm. Dynamic programming has only quadratic time. We've talked about edit distance problem, which again we've solved with a dynamic programming approach, filling a table whose last entry contains the actual information we've interested in, but gradually filling that. We've talked about parsing problem, syntax checking, that is, its special version of context-free parsing and the Koki-Younger-Kasami algorithm for solving that. And we've just finished talking about string compression, Huffman tree construction as a prefix-free code. So that's all from chapter 6 on algorithms.